So, as derived from the Greek language, the word trigonometry means measurements of triangles. Initially, trigonometry dealt with the relationships among the sides and angles of triangles and was used in the development of astronomy, navigation, and surveying. With the development of calculus and in the physical sciences in the 17th century, a different perspective arose, one that viewed the classic trigonometric relationships as functions with a set of real numbers as their domains. So that means their domain, the list of x values, is all real numbers. There I am. Consequently, the applications of trig expanded to include a vast number of physical phenomena involving rotations and vibrations, including the following: sound waves, light rays, planetary orbits, vibrating strings, pendulums, and orbits of atomic particles. So that's some of the ways that you will use trig if you take any of those kind of physics classes or beyond in college. So the approach in this text incorporates both perspectives, starting with angles and their measures. So we're going to first start talking about angles and their measures. So when you look, right here is an angle. So in trig, this is going to be kind of new to you. You're used to vertex, you're used to two line segments or two rays. And then right here in red is the angle that's formed. What's different is we have initial sides and terminal sides. So the way that you rotate matters. So going from here to here, from the initial to the terminal side, is different than going from the terminal side to the initial side. The way that you rotate the angle matters. So we're always going to have an initial side and a terminal side. So the majority, probably 95% of all of our rotations we're going to be doing are going to be done in a coordinate plane, which means an XY axis, right? A Cartesian plane, whatever you want to call it. In the coordinate plane, our initial side is always the positive x-axis. So when I say positive x-axis, do you know what I mean there? This is the x-axis. Over here's where it's positive. Over here would be the negative x-axis. So our initial side is always here. Positive x-axis. And then wherever we're rotating to, that's going to be our terminal side. So if we rotate it 90 degrees, that means the positive y-axis would be our terminal side. If we rotated all the way, like right here, 45 degrees, then I would draw a terminal side here. The terminal side is where we stop rotating. Our initial side, where we start rotating, is going to be the positive x-axis. Any questions about that? An angle is determined by rotating a ray about its endpoint. The starting position of the ray is called the initial side, and the position after you are done rotating is the terminal side, as shown in Figure 4.1. The perception of an angle fits a coordinate system in which the origin is the vertex and the initial side coincides with the positive x-axis. That's all fancy talk for everything I just told you. We're going to start on the positive x-axis. The vertex of our angle is the origin. And then the terminal side is going to be where it stops rotating. Okay? Such an angle is said to be in the standard position. So when we have the initial side here as the positive x-axis, we call it the standard position. Okay, positive angles are generated by counterclockwise rotation. Negative angles by clockwise rotation. So if I rotate in this direction, this would be counterclockwise. That is the positive rotation. So right here I'm rotating 90 degrees to get to here. That's a positive rotation. If I rotated negative 90 degrees, I'm going to go clockwise. Negative 90 degrees would put me here in the negative y-axis. So positive rotations are counterclockwise. Negative rotations are clockwise. So when you first hear that, you think, well, that's kind of dumb. All right, well, think about how we name quadrants. How do we name quadrants? This is the first quadrant because it's the first one you rotate to. It comes from trig. The first one you rotate to when you start at here and then you rotate around. Here's the second quadrant, the third quadrant, and the fourth because that's our positive rotation is going counterclockwise. Questions there? Okay. Angles are labeled with Greek letters such as alpha, beta, and theta. as well as uppercase letters A, B, and C. In figure 4.4, note the angles alpha and beta have the same initial and terminal sides. These are called coterminal angles. Okay, so there's our first kind of maybe new vocabulary word, coterminal. So think about what that means, right? Break down that word. Co means what? The prefix co. Okay, where else have you seen this?
Company.
Company? No, that's not a prefix.
Mutual.
Cooperate. Coexist. That means that it's a shared experience. What'd you say it meant?
Mutual.
Shared, right? So that's what I think of. So coterminal means they have a shared terminal side. They are coterminal angles. So when you look here is a rotation of alpha that put me here on this terminal side. This is a positive rotation. Right here is a negative rotation that ends on the same terminal side. They are different angles of rotation. One is positive, one is negative, but these are called coterminal angles because they have a shared terminal side. Coterminal angles. Okay? Look here. Here's another example of a coterminal angle. Angle alpha, we rotated, say that's 45 degrees. Right? Angle beta started here. It rotated 360 and then went another 45 degrees. But they have a shared side. So coterminal angles are always 360 degrees away from each other because I'm just doing another full rotation to get there. So if you think about it, let's just go through them. If this was 45 degrees, what are some coterminal angles with 45 degrees? Well, we could add 360, which means 405 degrees would be coterminal. I could do 360, 360, and 45. So that would be 720 and 45, which is 765. And I could keep going. Those are all coterminal angles. Or I could go in the negative direction. You could think about subtracting 360 from here. 45 minus 360 would be negative 315 degrees. That would be coterminal. It would have the same endpoint. Or you could go negative 360 and then negative 315, right? You can add or subtract 360 to get back to that same terminal side. So you have to know what that is. That's going to be important. Coterminal angles, they have a shared terminal side or a mutual terminal side. And they're 360 degrees away from each other. They're one full rotation away. And I'm sorry if you watch this back later. At least you can hear me. I got to get back to writing on my iPad. All right. Used to measuring angles is in degrees. You've seen degrees. You know what 90 degrees is. You know what 360 is. Okay, but actually, degrees are not all that great for doing algebra and doing math with, because the degrees have a unit attached to them. 360 degrees, 70 degrees. And so they're not unitless, and so they don't follow the general rules of algebra. So that's actually just one way that we can rotate or talk about the rotation of an angle. But like, who determined what 1 degree was, and why are there 360 of them in a circle? Like, where did that come from? Y'all know? Don't know? All right. So think about. This is me letting you explore. Think about where you think it might come from. Like, what's 360 kind of close to?
Oh, the year?
Yeah. And so originally they thought there were 360 days in a year. That was one full rotation around the sun. There's actually 365 when they got more precise with their measurements. And they liked 360 because 360 is very easily divisible. Because they didn't like decimals and fractions. They couldn't deal with them. Think about 360. Can you divide it by 2? Divided by 3, 4, 5, 6. Yeah, it's a very easily divisible number. So that's why they chose 360. Well, that's just kind of strange. So, right here's another way we can talk about measuring angles that's much more conducive to doing other kinds of math with it. It's called radian measures. This is another way to measure angles that's not in degrees. You guys remember seeing radian measures in geometry? Okay, you did it. You had to convert from degrees to radians and radians to degrees. Okay, but you probably didn't do any more than that. We're going to be doing a lot more with radians in this class. So we're going to first talk about what a radian is, and then I normally do a demonstration, but I don't have my rope with me, and I don't have my circle drawer. So I found a YouTube video that's going to do basically what I would have done anyways. So we're going to read this and we're going to watch a video. The measure of an angle is determined by the amount of rotation from the initial side to the terminal side. One way to measure angles is in radians. This type of measure is especially useful in calculus. To define a radian, you can use a central angle of a circle, which is an angle whose vertex is the center of the circle as shown in figure 4.5. So this kind of looks confusing to start with, but you can see here, think about this being a circle. I'm rotating around a circle. All circles have a radius. That's the distance from the center to the outside edge. Radius. So the bigger the circle, the bigger the radius. The smaller the circle, the smaller the radius. But every circle has a radius, r. We're going to take whatever that radius is, and we're going to go that same length along the outside of the circle. So if this is a radius r, this arc length here is also r. This measurement and this one are the same. So I've rotated one radius along the outside. It's called a radian. Right? That's where radians come from. So let's watch this video. Maybe they'll do a better job explaining it than me. And say this is useless. And that's fine too. Is everybody good with 2 pi radians being 360? It's the same measurement. So if I cut that in half, that means in 180 degrees there are pi radians. Now when I think about it from here, I can divide this into different sections. So like if I divided pi into 2 sections, right, that would be 2 equal sections. That would be divided here. And so if the entire thing is pi rotated, what would this be? I've cut it in half. So this would be half of pi, which we write as pi over 2. It means the same thing because I found half of it. Okay? Now what if I half? What would this be? If this was pi over 2, pi over 4. If you half a pizza, think about it. I'm always going back to pizza. I got half a pizza. If I half of it, now I've got 2 sections. What if I half again? Now I have 4 pieces. It's still pi in total, but now divided into 4 equal pieces. So this would be a fourth of pi. This would be another fourth, so that's 2/4 of pi, or half of pi. This would be 3/4 of pi, and then pi. But we don't normally write them like this. We don't write the fraction times pi. We normally just move pi to the numerator because it's the same difference. So here this would be pi over 4. This would be 2 pi over 4, which is pi over 2. This would be 3 pi over 4. This would be 4 pi over 4, which is pi. So what would this one be? Y'all follow my fractions or no? Because this is what we're fixing to get into. And I know we hate fractions. That's why I'm trying to build it. Go ahead, Hall.
Like you're telling me like the whole thing?
Mm-hmm.
8?
Well, yeah, there's 8 pieces total. Think about this. This is 1/4, 2/4, 3/4, 4/4, 5/4, 6/4, which is 6/4 is 3/2. This would be 7/4. This would be 8/4, which is 2. We follow?
No,
9/4, 10/4, 11/4, 12/4, 13/4, 14/4, 15/4, 16/4, which would be 4 pi. I went around twice now. And I can keep going. Or I could go the opposite direction. This could be negative pi over 4. Negative 2 pi over 4. Negative 3 pi over 4. Negative 4 pi over 4. I go in the opposite direction. I'm trying, guys. I mean, I'm telling you, I'm trying. I'm laying it out there. I'm going slow.
I'm just confused.
Why?
Because like some of them say like power 4 and some of them have like 3 power 4. Like, I mean, I don't know why it's confusing me. It just is.
Okay, so you drive it down the interstate, right? And, you know, they got mile markers up for every mile. Well, imagine that if they went every half mile, because like Georgia does, or not Georgia, maybe. Some states have mile markers every half mile. I don't know if it's Georgia, Florida, but some states have them every half mile. It's like you could see mile marker 250, and the next one's 250 and a half, 251. 251 and a half, 252. Because I'm taking that normal mile and I'm cutting it in half. When I just cut it in half of half. So now instead of halves, I'm dealing with fourths. What happens if I cut fourths in half?
Yeah, small ones.
Which is what?
4s and halves.
If you cut fourths into halves. If I cut fourths, think about pizza. 4 slices. This is a fourth, a fourth, a fourth, a fourth. If I cut
eights.
yes. If I cut fourths in half, I get eighths. So fourths and halves is eighths. If I cut eighths in half,
16.
cut 16ths in half. Do you follow? So that's all I'm doing here. I'm doing it again. I'm patient. It's a new year. Right here, we've talked about all the way around is 2 pi. If I cut that in half, 1 pi. Right? I want to focus on this because 1 pi is a lot prettier to deal with than 2 pi. So right here, I'm starting with pi. If I cut pi in half, because right here's the pi, cut it in half. So this is how much? Half of pi. This would be 2 halves of pi. Well, 2 halves, what's 2 over 2? It's just pi. It's just pi. This would be, so this is 1 half, 2 halves. This would be 3 halves of pi. This would be 4 halves of pi. 4 over 2 is 2 pi. And this would be 5 halves of pi. 6 halves, or 3 pi. 7 halves. 8 halves, which is 4 pi. Now if I take this, which is in fourths, and I divide those into halves, so this is still pi over 2. It didn't change. But now I've got a line that's halfway between the half. So I'm half of half.
Yes.
What is it?
I don't know.
Half of half. I've got half a pizza, and I half it.
Half and half. 4s.
So half of pi over 2 is
8s. Wait, is that right? Oh, pi 4?
pi over 4. Pi over 2. So think about this. Pi over 4. This is 2 pi over 4. 3 pi over 4. 4 pi over 4. 5 pi over 4. 6 pi over 4. 7 pi over 4. And 8 pi over 4. And when I reduce all these things, this is still 2 pi. This is still pi. This is still 3 pi over 2. It's the same rotation as it was before. It's just now been cut in half. But this is the easy one. Halves and halves is easier to make. Right? But we don't have to cut it into halves. That's what we're going to here. What if I wanted to take this, I know that this is pi. What if I wanted to cut it into thirds? So this would be pi over 3. This would be 2 pi over 3. 3 pi over 3. 4 pi over 3. 5 pi over 3. 6 pi over 3. 2
So
pi.
it's kind of just like, it's like the number on the top's kind of like labeling the pieces almost.
That's how many pieces I've rotated over.
Yeah.
I've rotated 1/3 of the way, 2/3 of the way, 3/3 of the way. Yeah, it's how many pieces. That's exactly what it is.
Okay.
That's exactly what it is. Now, if I take this that's in thirds, and I halved it. So this is a third. What's half of a third? A sixth. So this would be pi over 6, 2 pi over 6. 3 pi over 6. Well, what's this? What's 3 over 6? We're back here. So this is 3 pi over 6. This would be 4 pi over 6. 5 pi over 6. 6 pi over 6. Or just pi. 7 pi over 6. 8 pi over 6. 9 pi over 6. Which is 10 pi over 6. 11 pi over 6. 12 pi over 6. I know, fractions, right? Hate them. Get used to them. Okay? Whew. Now, what we're looking at next are the quadrants. So we talked about there are 4 quadrants. 1, 2, 3, and 4. All right, let's first talk about it in terms of angles and degrees. So remember, this is my initial side. I'm starting here. So how much do I have to rotate to stay in quadrant 1 in degrees? Anything between 0 and 90 degrees puts me there. So this is 0 to 90 degrees. Now in radians, what is that? What was 90 degrees? Half of pi. This was a complete pi here, so this was half of pi. So in radians, if I rotate from 0 to pi over 2 radians, that puts me in the first quadrant. Okay? Now, if you look at the book talks about it a little bit fancier, the way they write it. Right? But it's the same ideas. Right? The book says, quadrant 1, your theta, that's your angle of rotation, must be between 0 and pi over 2. That's what we just talked about. But that's all this is saying. Right? That's what we've done talked about. Right? When we look at quadrant 2, how much do I have to rotate in degrees to get to quadrant 2? It has to be more than 90, but it has to be less than 180 in degrees. And then in radians, what is that? That's going to be more than pi over 2, but less than pi. Quadrant 3 is what in degrees? More than 180, less than 270. And in radians, that would be more than pi, less than 3 pi over 2. Have to remember this was 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2. And then quadrant 4 has to be between 270 to 360. Or in radians, that is from 3 pi over 2 to 2 pi. So my directions here for the next 3 problems. We want to sketch this angle and we want to find a coterminal angle. So this is in radians, right? 13 pi over 6. So I need to know what quadrant does that put me in, and then name a coterminal angle to go with it. Okay, so you don't have to do all these details I'm fixing to do if you start learning where these angles are. Like for me, I know where this is right now, but we'll talk about it later, how I go through that process. But let's think about how could you figure out where the angle's at. So the way I think about it, it's dividing to 6. Right? We've talked about dividing into 6 before. If this is 1 full rotation, 1 pi, puts me here, and I'm dividing that pi into 6, that means I need 1, 2, 3, 4, 5, 6. That's my 6 over 6. So I'm going to think about dividing that here. I've got there, there. Oh, can you draw a line? No, I can't. There. That's okay. Okay? So now dividing to 6. So the way that I first learned it, the way I thought through it, this would be 1 pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, 5 pi over 6, 6 pi over 6, 7 pi over 6, 8 pi over 6, 9 pi over 6, 10, 11, 12 pi over 6, which is 2 pi. 13 pi over 6. That puts me here. So a rotation of 13 pi over 6 puts me in the first quadrant. So if it told me to sketch it, what I would be looking for is here is my initial side, here is my terminal side. That's sketching the angle. Now, how did I get to that angle? I rotated all the way around 360 and got back there. Right? If I had to draw the rotation, that's what really happened. So I have now sketched the angle. I put in the correct quadrant. Now, what's a coterminal angle that goes with it? So coterminal means it has the same terminal side. Right? Well, what if I didn't rotate all the way around? What if I just rotated to there straight away? Then how far of a rotation would that have been? That would have been 1 pi over 6. That has the exact same ending point, and it's coterminal to 13 pi over 6. Okay? Another way you could find that coterminal angle is to take your original 13 pi over 6 and you can add or subtract 360. Okay, but this is not in degrees. So what would I need to use instead of 360? 2 pi. I could add or subtract 2 pi to this to find the other coterminal angles. So if you put in your calculator, if you put 13 pi over 6 minus 2 pi, you get pi over 6. Because what your calculator's having to do is get a common denominator. Right? So this would be 13 pi over 6. This would need to go over 6, so I had to multiply by 6. So that becomes 12 pi over 6. 13 pi over 6 minus 2 pi, just written as 12 pi over 6, is 1 pi over 6. Is this the only coterminal angle? No, you could have subtracted 2 pi again. You could have added 2 pi. Right? There's an infinite number of answers, but they're always 360 degrees away, or 2 pi radians away, depending on what we are measuring in. So for me, the way that I work that, I know 13 pi over 6. So when I have to figure out what quadrant it's in, I don't do this anymore. Right? That's a good way to start, to think through it, rotate it for yourself. But I know that this is bigger than 2 pi because I can go over 6. 2 pi would be 12 pi over 6. So I know this is more than 2 pi. So in my head I can go, okay, 12 pi over 6, 13 pi over 6 puts me 1 more over it. I just know that. Or what I could have done initially, I could have said, well, let's subtract 12 pi over 6 and put me at pi over 6 because they have the same terminal side. So I know what quadrant to rotate to without having to count all the way around. Okay, the next one tells me to draw 3 pi over 4 in the correct quadrant and then find a coterminal angle. So again, this is my initial side. So what do you guys think about 3 pi over 4? Second quadrant? How do you know it's in the second quadrant?
Because it's greater than 90 degrees and less than 1.
Okay, it's greater than pi over 2, but it's less than pi. That's 3 pi over 4. So that's going to actually put me here in the second quadrant. And this will be my rotation. All right, you can go through what we did before. There's nothing wrong with that as you're learning. You can know that this is pi. So if I need force, I need to divide this into 4 equal sections. And so this would be 1 pi over 4, 2 pi over 4, 3 pi over 4, and 4 pi over 4. Either way, there's nothing wrong with that. You just have to get you a system where you understand it. Okay? Ooh. Now, what is a coterminal angle with 3 pi over 4? So what I can do is I can take 3 pi over 4, and I can either add 2 pi or subtract 2 pi. Either way. This time the book subtracted 2 pi, so I'm going to add 2 pi. Just because. It doesn't matter. So if I take 3 pi over 4 and I add 2 pi, that's going to be 3 pi over 4 plus 8 pi over 4, which is 11 pi over 4. To get that rotation, I'd have to rotate 360, which is the 2 pi, plus another 3 pi over 4. Right? 8 pi over 4 plus another 3 pi over 4 puts me at 11 pi over 4 for that rotation. Again, is that the only coterminal angle? No. Questions there?
Yes.
Okay.
How did you go from adding 2 pi over 1 to 8 pi over 4?
I got a common denominator. Whenever you add fractions, you have to get a common denominator. So 4 and 1, the common denominator would be 4. So I need to multiply on top and bottom by 4.
Okay.
1 times 4 is 4, 2 pi times 4 is 8 pi. Anything else? And like I said, if you got a calculator, it'll do that for you too. Don't think you have to do it all in your head just because I do it in my head. You can literally put this directly in your calculator. You know, as long as you understand what's happening. Really good. Anything else on this one? All right, so hopefully you are finished or you got somewhere close to being finished. So here's what A looks like. It should be in the first quadrant. Your coterminal side, this is a little tricky. If you subtract 2 pi, that gives you pi over 4. This would be a positive coterminal angle. So in order to find a negative coterminal angle, I would need to subtract 2 pi again. So for me, these are the two coterminal angles I got. You could have gotten 17 pi over 4, but you would still need to have negative 7 pi over 4. Because subtracting 2 pi over 4 still gives a positive coterminal angle. But you would have to subtract it again. You would need one of these two and this one. Does everybody understand what I'm talking about? To make it be positive and negative. And then same thing here. This is a little bit easier though. This is where you draw it. If you subtract 2 pi, you get negative 7 pi over 3. If you add 2 pi, you get positive 5 pi over 3.